Hey, welcome back to Fan Mama Physics. In this video, we're going to talk about similar polygons. So this is building off of building off your scale factors. So for enlargements and reductions, but this time we're going to apply it to shapes instead. Okay, so I'm going to move that over here. And, okay, so guess what? I do have a board game I would like to show us today. I'm going to do this a little bit differently because this board game, it was very hard to find a board game in which it really matched what I wanted to show us. But this one I get to use to show us why sometimes things don't work out. So, without further ado, I think you're going to like this box cover. It's called Unicornus Night. It's a very anime looking kind of board game. It's a cooperative adventure game, and it's based off of the creators actually even made a little manga out of it. So guess what? I'm going to transfer over to this other phone here. Alright, so right now you should see part of the game that I've set up. So here I'm going to move this here to give you a better shot at the board game cover. Unicornus Night looks very pretty. Okay, and next up we have the I also wanted to show you the rule book, but it's because in the rule book, there's a rule book, there's a part, they actually made a little story to it, and there's some very nice manga graphic drawings here to show you the story. I know some of you are gonna like that, so I had to show you. You know who you are. Okay, so that was it. It was part of the story, and essentially what happens was the castle, the palace, got taken over by this this emperor person. I don't remember exactly. And then, as the princess trying to reclaim the throne and to save his, I guess the father's dead, her father or something. She is trying to reclaim the throne by moving through the map and destroying all of his, all the person's minions. Or not minions, there's people that help him out. So, this is what the game is kind of about. So, I'll quickly go through, talk about it. Here's the different princesses. You can be a warrior princess, tactician princess, lucky girl, or social. You get a princess to work with, and essentially what she's going to do is she's going to dart towards this other guy on the other side of the map until you either feed her up with people that she has to carry, or you kind of have to make way for her, or kind of cleave out the path for her so she doesn't get herself stuck or ramming herself into crazy people. So, let's take a look at the map. Ooh, hey, I forgot to show you some characters. So yes, you have different helpers. These are you. You could be this person. Let's set up the camera. Hopefully I can edit all this out. We'll see. Okay, so these are different people you can be. You look very nice. Nice drawings, very pretty. They have yes. Yeah, they're very nice drawings. Who's my favorite? I like this dwarf guy for tactics reasons, because he can just, his defense stats are really nice, because when the other team goes aggressive on you, you can just roll a really heavy defense dice and still be able to do a lot of damage. So I really like him for tactics reasons. And then you have some people from the other team. So yeah, you have a vampire. Look at the art's so pretty. There's a dragon, there's a princess, etc. My favorite enemy is this pair. They're called the twin stars, meaning that if you only kill one on a given turn, the end of the turn, the person is reborn if the other twin star is still active on the map. So essentially, you have to find a way to kill them both at the same time. It is pretty fun. Interesting. Okay, so why did I choose this for polygons? Because if you take a look at this map, notice the tiles themselves are in the shape of a hexagon. So then, the reason why it's not that great is in terms of showing the polygons is because I wanted to find a game in which the board scales up in terms of number of players. This doesn't quite do that, but I get to show you something about polygons and I want to make a very clear point about. So polygons, for similar polygons, you have to make sure that even though you have a scale of polygon, all the angles as well as all the sides must be, all the angles must be the same when you scale up a polygon, as well as all of the sides have to be proportional for a polygon. Very specific. If you take a look at why. Let me take out part of this map, okay? So notice you have a hexagon shape. If I just combine all these tiles, the bubbles shapes don't really help out, but you can kind of imagine they're kind of like hexagons. And if I wanted to make the map bigger, even though, so if I make this map bigger, I might just add these guys. They're oriented and poorly, but let's make do. Okay, so notice I extend the map like this. I put those back. I still have the same angle here. So this angle here, this side of this polygon is no longer hexagon, by the way, because not all sides are equal. So here is a specific angle, which is the same as what we had before. So is this angle here. Okay, notice this angle here. This angle here is still the same. This angle here is still the same. And so is that angle, this angle, and this angle relative to the original polygon that we have here. Okay, the angles are still the same. But notice that I've now made one side longer. Because the sides are longer, this polygon versus this polygon, these are no longer similar. So for you can kind of see how the it doesn't quite scale very well. You know, and when we get to triangles, the case will be a little different. But for polygons, all the angles must be the same for similar polygons, as well as all the side lengths must scale up proportionally. So for example, this guy, this polygon you see, is similar to this base polygon, this tile that I have over here. But if I add these tiles here to make this polygon bigger, even though the angles of my polygons are the same, the sides are longer, so this polygon is no longer similar to this guy. And that's kind of what I want to emphasize in this lesson, because for polygons, you need both criteria in order for the two polygons to be similar. Okay, so that's the gist of the game. It's a really fun. I enjoy this one a lot. It builds a lot of story, and I know a lot of you like anime, so this is another reason why I picked this board game to show us. Hopefully you enjoyed it, so hopefully I didn't take so long either. I'll get back to the lesson, so let's put this board game away. Yay! Let's get started. So that was the game. So coming back to here, we have Similar Polygons. This is 2 videos, by the way. This is part 1 and a part 2. Let's take a look at an example here of a quadrilateral. So let's just go back here. 2 key points. For properties of similar polygons, you need to make sure that all the angles are equal as well as all the sides are proportional. You must have both of these conditions in order for your polygons to be the same. So let's take a look at this one down here. So let's take a look at how these guys are similar. First of all, we have the angles. Notice that all the angles have a different symbol attached to it, and you'll see a corresponding symbol on the other polygon in which the same symbol corresponds to the same angle. So for example, let's take a look at angle A. In this smaller polygon, it is this little shape here. For this other polygon, the bigger one, it corresponds to P. And notice I put a little angle and the symbol P just to show that's the angle we're talking about. For B, this guy, that's similar to Q, so I'm just going to put that one here. For C, this guy shows that little symbol, which is going to be similar to R. And last but not least, D is going to be similar to S. All right, so here we will see how the sides are proportional by doing a ratio test. So a ratio test is I'm going to take one length from this side of my, from this polygon. I am going to take that and divide it by the corresponding side length on my similar or supposedly similar polygon. So that would be this one over here. So let's take 1.5 divided by 2.1. Okay, so putting that into your calculator, that's gonna give me 0.714. 0.71, and I'm going to put ... just to show the decimal continues. Now, if all of the side lengths are proportional, that means the ratio of the smaller one, the smaller side length to the larger side length will all give us 0.71 for the ratio. Okay, so let's try another one, BC, which I'll use this color. Okay, BC is 3, and the corresponding one is this side length. You might be wondering, oh, Miss Lee, how do I determine the lengths are this corresponding to one another? The one thing you want to check is you check the angles. That's the easiest way. Notice that from B to C, that is between this double angle here and this little cross angle over here. Then in my similar polygon, in the bigger one, I gotta choose a side length corresponding to the same side, the same angles of my polygon that are the same. Okay, so I'm choosing it based on the angles. So that's why it is BC to QR code 3 over 4.2. And notice I'm not putting in the units, because if I put the units on top and the units on the bottom, the units actually cancel out. Oh hey, I also get here 0.71. 0.71, but this is 4285. I wonder if that's the same, exactly the same as other one. Oh, it is. Okay, cool. All right, it's exactly the same. If you even continue the decimal, it becomes the same. I was curious about that. All right, so next one is CD. CD. Oh, it's this one. CD to RS. And notice that even the direction is the same. Like, it's the same direction. C to D going this way, RS going that way. So just good to be very specific there. Anyways, we have a similar ratio, 3 to 4.2. Okay, and that's of course it's going to be the same as what we had before, so I keep that as that. Last but not least, we have, going to be in red, DA. Oopsies, DA to SP. So that is 2 centimeters to 2.8. Okay, and I don't have space to write the units, so, but the units cancel out. Hey, it also gives us 0.714, and also as well as all of the trailing decimals are exactly the same, meaning these sides are very, very, very much proportional. And if you recall some of the earlier lessons, you will be able to say, here, let me ask you this. Maybe a good time to pause. Well, not yet. Let me ask you the question first. What do you think this number represents? Okay, the 0.71. What do you think this number represents? There's a specific name for it, and we talked about it in our previous 2 lessons. Give you a chance to pause the video, think, and if you're thinking scale factor, yes, you are right. This is the scale factor. This is called your scale factor. All right, that is a scale factor between the smaller one to the big similar polygons, and vice versa. So depending on which one's the original, which one's the copy, you have a reduction or you have an enlargement. If this was your original, this is your copy, then yes, you do have an enlargement for this example. Whoopsies. Okay, so let's move on. Now you have an idea how to do all these checks for the side lengths to test for similar polygons. Here, let me give you a scenario. I give you a bunch of rectangles. Take a look at all the rectangles. There are 3 of them. We don't know which ones are similar, but we do know that they all have the same angles because, well, duh, all the angles are 90 degrees, right? So there's no way for them to not have the same angles, okay? Anyways, you get the idea. Because yes, they are all 90 degrees to one another, and what we want to do is we want to determine if the corresponding sides are proportional as well. So your task, I'm going to leave this for you to try, is you want to figure out which of these rectangles are similar. Here's a test that we have here below. They did a test for us. They compared A, B, C, D. They compared this one. Let's label them. Actually, triangle, rectangle 2. Oh, actually, let's say this is 1, this is 2, this is 3. So what do they compare? A, B, C, D. So that's they compared 1 and they compared it to number 2. Okay? And this comparison is comparing 1 to 3. And this comparison is triangle 2 to triangle 3. All right. So your task is, using the numbers that you see in this diagram, you're going to figure out these proportions and whether or not which rectangles here are similar. Good time to pause the video. Okay, my turn to do this one to wrap it up. Okay, so we're comparing 1 to 3, these two here. So then we start with AB. AB here is 8.5. Okay. And JK, I am joking, ha ha ha. Well, here's interesting, because they want you to compare to this side. Seems like they would be similar too. But we are not given that side, but because we have a rectangle, the other side is the same. So we just divide it by 5.25. And that's going to give us 5.25, 1.6. 1.619 dot dot dot. All right, try it out for BC, just like us. 2.5. So that's this length versus KM. KM is here. 1.5. Oof, I don't know, man. That doesn't look very similar to me. Okay. Oh, I get 1.66666 repeated. These are not equal. So it doesn't look like 1 and 3 are going to be similar. All right? But let's take a look at 2 and 3. 2 and 3, we have EF. Okay, EF is this guy over here, which is going to be exactly the same as this side. 8.4. 8.4 divided by JK again. I am so joking. 5.25. 5.25 gives us 1.6. Not bad. FG. FG, where are you? FG, 2.4. Force due to gravity. Just kidding. Over KM, which is 1.5. That doesn't look too bad. It looks quite nice. Hey, yay, we got 1.6. Perfect. We do get 1.6, which means this, we have equal proportions. So the side lengths are also proportional as well as the angles. So we say that the rectangles 2 and 3 are similar. And I forgot to mention 1 and 2. 1 and 2 is not similar because you can take a look that these two are not very similar. And when we say similar, I'm talking about the proportions in terms of the ratio and the decimals. All the decimals have to be exactly the same. Okay? If it's 1.01 versus 1.04, even though they look very similar in terms of numbers, they are not similar at all. Okay? So just be careful with that. And guess what? I actually want to just wrap it up with this last example here. I'm not going to do I'm going to do the next one in the next video. But here, take a look at this. Here you're just going to test for, now imagine that you do have a known side length. I wish I had a diagram for this. Here, let me draw a diagram quickly. So I drew a few diagrams here just to help you out. For example, A, we have these two similar rectangles, in which this side is 4. This is similar to the 6th side. And 16 is on the smaller rectangle. You want to find out the length of this larger one here. You might be wondering, hey, Miss Lee, how do you figure out which side is which? Well, first of all, we divided, in this ratio, we divided the 4 by the 6. That usually means you're dividing two similar sides. And it looks like the 4 is the smaller side, 6 is a bigger side. So I know that I have to put the 4 on the smaller side, and then a smaller polygon, and the 6 on the bigger polygon. Then you look at the other side of the equal sign. The other side of the equal sign is 16 on the bottom. Because 16 is on the bottom, it is on the same part of the fraction, it's in the denominator, is the same as where the 4 is, which corresponds to the same polygon. And so you want in order for the ratio to be the same, the ratio to 4 to 6 has to be the same as 16 to whatever this one is as well. So that's how I determined which side is which, and I did it for both B and C, in which the variable AB or A or OP, overpowering, is going to be the one that is labeled as a question mark, just to help you out a little bit, but hopefully you get a chance later on to figure out how it works yourself, okay? And algebraically, all you have to do is just figure out what AB is. All right, so maybe this is a good time for you to pause the video to try out all of these yourself. And of course, I will do it to show you the solutions. Okay, so let's figure out AB. All I have to do is to solve this algebraically by multiplying both sides by 16. I get AB, that question mark side is 6 divided by 4 times 16. Plug it into my calculator. Oopsies. I get 24. And also, no units were given to me in the question, so I don't need to worry about putting in the units for that one. Okay, next up we have this guy. Hey, guess what? If you know my little trick, or you watch those challenge videos in the algebra section, you know you can just flip both sides of the equation. So if you want to do that, you can go ahead and do that first. But I'm going to do the longer way. Oh, I hate the longer way. Here, let me rewrite this. This is 12.5 over A. Let me just calculate the other side. 7.5 divided by 1.5. This is going to give me 5. All right? So I know this is 5. The next step is for me to multiply A to the top. Remember, I cannot have a variable on the bottom when I'm trying to solve for it. On the bottom of my fraction, so I'm going to multiply both sides by A. That gets rid of this guy. I get 12.5 equals to 5A, and then I can divide both sides by the 5 to get rid of my 5, leaving me with A is equal to 12.5 divided by 5. That's going to give me 2.5. Okay, so that's A. Double check if it makes sense. 2.5 should be smaller than 12.5 since the other ratio part, the 7.5, is bigger on top. The numerator is bigger. And if you did it the flippy way, so you flipped both sides of the equation, then you're going to get 12.5 on the bottom. You just have to multiply that up back to the top to give you what your value of A is. Okay. And last but not least, we have C. Hey, the variable's on top. This is easy. We just have to multiply both sides by 1.8. And that's going to give us OP is 6 divided by 1.3 times 1.8. This is 8.30, 8.3. I'm just going to leave it as 8.3 because it rounds really nicely. And after you do all these questions, it's always good to check. Take a look at OP, overpowering. It should be bigger than 1.8 because notice that 6 is bigger than 1.3. So the top has to be bigger. We just checked B. I forgot to check A. So let's double check A again. Notice that for this ratio here, 6 is bigger than 4. AB must be bigger than 16. We got 24 for AB, so that checks out. All right, so there you go. This is the check for essentially whether or not your polygons are similar. In the next video, we'll be doing more examples. So thank you for watching this video. Hang on, one more video coming. It's going to be shorter, so thank you for watching. Good luck. See you next time on Fan Mama Physics. Signing out.